So can you see it? Yes.
Yeah.
Good. So in the previous class, right, we did this Karush-Tucker conditions. And right now, as I mentioned, right, so welcome to our class 4. So today I got some issues with the connection. So if something freezes or anything, let me know, right? So I can try to fix it. But right now I'm with a different connection. So usually I have a cable. So right now I have just a mobile connection because my usual connection failed, okay? So now I have this property of indirect utility, right? So we studied previous class properties of demand, and now we have the properties of indirect utility. So the properties of the indirect utility, remember what is the indirect utility? Is just this number, which expresses how much welfare the consumer has at a given budget, right? So this is the welfare assigned for a given price and income, right? So price and income gives you a budget, and then the consumer maximizes, obtains a demand bundle, and then you put it inside the utility, and this gives you the indirect utility, right? So the indirect utility is a function of prices and income. Now, this is important because this captures the level of welfare you get from a particular price well situation. So this indirect utility, as you see, this is actually ranking different prices, right? For instance, if you have a tax situation where you have two different tax schemes, then using the indirect utility, you could actually know which utility, tax scheme is better than the other, okay? So in particular, this indirect utility, as opposed to the direct utility, doesn't rank the bundles, right? It ranks the budgets. Do you understand? So because this is a function of prices and income, it produces a ranking or a utility over prices and income, right? So this ranks budgets as opposed to bundles of baskets of goods. Do you understand? So this, in a way, is the dual object, right, of the direct utility. That's why it's called indirect utility. So in short, the indirect utility, so let's formalize it a little bit here, is a function from prices and income, right, to the reals. Okay. So this is a form of ranking prices and income. Hence, budgets. Okay. So this thing basically ranks budgets basically through a utility, but this utility is not defined on the space of choices, it's defined on the space of budgets. Okay, hence the name. And essentially, one important observation, imagine you have a demand correspondence, right? You pick any two elements of the budget correspondence. If you put it inside the utility, it will give you the same utility, right? So here, it doesn't matter whether the maximizer is a set or a singleton, right? It doesn't matter. Any element of the budget, any element, sorry, of the demand correspondence will map to a single utility, because this is the set of all the utilities that are maximizers, right? So it's a single value. So this object here is never set value. This is always a function, okay? That's the point I'm making. So as opposed to the demand correspondence, the indirect utility is always a function, right? So it maps a price and income to a number, not to a set, okay? So this is always a function. So, okay, good. This is always a function. Now, the way to write is equivalently take the demand correspondence, right? Imagine this is a function, right? And just put it inside the U, and then you get a number, right? So BPW. Now, suppose U is a continuous utility representing some locally non-associated preferences defined on the consumption set. And now, essentially, the indirect utility has the following properties, right? Just due to local non-association and continuity. First is homogeneous of degree 0. So remember the previous class where we said basically that the demand never changes with the scaling up of prices and income, right? And we call this homogeneity of degree 0. Now, if the demand doesn't change, the welfare you derive from the demand doesn't change as well, right? So the indirect utility is as well homogeneous of degree 0. This, remember we discussed about money illusion. So the indirect utility doesn't react to nominal changes in prices and income. It only reacts to real changes, so relative changes of the prices and income. Okay, do you understand? So first thing. Second thing, so the indirect utility is strictly increasing in income and not increasing in prices. Okay, so it means that basically as income grows, you have more welfare weekly. Okay, so you can see that this is a consequence of what property? Of continuity or local non-association. This is clearly basically a property of, as you can see, local non-association, right? Because as income increases, the budget is expanded, and that means there is a ball, you know, in any previous maximizer, such that there is something that is strictly better. Okay, so local non-association means that as income increases, then welfare increases weekly, and it's not increasing in PL. Okay, so that means that sometimes, right, when things get cheaper, right, then of course the utility is going to increase. But if prices increase, then the utility is going to decrease. Of course, you have the weekly part, because some changes of prices won't make a difference really, right? And this is especially the case when you have corner solutions. Okay, so therefore the non-increasing. Okay. Finally, there is some shape constraints of the indirect utility. In particular, the indirect utility is something that is called quasi-convex. In fact, Mascolel, and this results from Mascolel, defines already what is quasi-convex. And the meaning of quasi-convex is basically the following, is that if you take the set of prices and income, right, such that the indirect utility of such price and income is less than or equal than V bar for any V bar, so for a fixed level of indirect utility, and you basically observe this price and income set, right? That set is convex, okay? So if that happens, then you declare the indirect utility V to be quasi-convex, okay? So essentially this property right now is just a property that is geometrical. It doesn't have really any deep behavioral meaning, except that it's just a property of maximizing a utility subject to a linear budget, right? So when you do that, you end up with this object that is quasi-convex. And in the end, when we match this theory with the theory of expenditure minimization, if you remember this from undergrad or master classes, we will be able to link this quasi-convexity of the indirect utility to a more important property, which is the concavity of the expenditure function, right? So this stage, this is a property that is inherent, basically. It's kind of the mirror image of the fact that the demand correspondence is upper continuous at compact value, right? In this case, you're going to get this extra thing, which is the quasi-convexity of the indirect utility. So this you always get, irrespective of whether the demand is quasi-concave or not. This is important. So the indirect utility is always quasi-convex, irrespective of whether the utility is actually quasi-concave. Okay, so this is beyond that. Okay, it's just a mathematical property coming from the fact that you're maximizing in a linear budget. Okay, and then finally, the indirect utility is continuous. So we already said this before, right? So basically, I said that our theory, because of continuity of the utility, is ruling out discrete jumps when I change my price by a bit or my income by a bit. So if I say I increase the price by 1% and my income by 1%, it will never be the case that my welfare discretely jumps to minus infinity, right? So nobody gets so angry that says by 1% of taxes, I now, my utility is minus infinity. Here, we're ruling out that you only have a continuous change in utility. So your utility will change also by a bit, okay. So now, in particular, right, the only thing that requires a proof really is the quasi-convexity, right? This proof is actually very geometrical, so it doesn't have really any behavioral meaning, but let's do it quickly because it kind of helps us to use some properties and to use some definitions, right? So it's a good practice for proof techniques. But at this stage, this is really a property that doesn't have much behavioral meaning. Again, we will connect it at the end with a full chapter with expenditure minimization and the concavity of the expenditure function. in which case this thing will make more sense. So I understand that there is not much intuition at this stage, right? But bear with me, okay? Now, we're gonna prove that this thing is quasi-convex. So you know already the definition. So I just want to show basically that the set of prices and income is a convex set. So I start with any V bar, which is a fixed number. So you can imagine a number such as 1. This is any arbitrary number, right? So I'm saying the indirect utility for this given price and income is less than or equal than 1, right? Now take another element of that set, P prime W prime, that is also less than or equal than V bar, which is 1, right? I'm fixing 1. It can be any other number. Now I take a convex combination of the two prices and income. So alpha P plus 1 minus alpha P prime and alpha W my 1 minus alpha W prime. You understand what I'm doing? So basically I'm trying to show that the two elements in this set of things that are dominated, right, by V bar are gonna be inside the same set. So what it remains to show, obviously, is that V of P double prime comma W double prime is less than or equal than 1. Do you understand? Right? That's my objective. So I want to show it. Now, it turns out that this statement is equivalent to the observation that for any X such that is affordable according to the second budget, the third budget, P double prime. So take any X that is inside that budget. Now, if that's the case, basically, you remember that U of X is less than or equal than if this is the case, essentially, right, that this is the assumption that I want to show, that Ux is less than or equal to U bar, basically it will mean the following, right? So if I have that something is inside this third budget with a double prime, then it has to be that, of course, the convex combination of the original budgets times X is less than or equal than the convex combination of the incomes. Now, this means that either there's two situations, right? P times X with original price is less than or equal to W, or P prime times X is less than or equal than W. But it can also be both, right? If the former inequality holds, then we know that the utility of this object has to be less than the maximum utility achieved under the first price and income. Do you agree? Right? Which happens to be below the 1. And then we have the result. And then the second case is, of course, with the second income and second price with the prime, it has to be that the utility that is inside the budget has to be below the maximal utility according to P prime, in which case this is also below P bar or 1. So that means that this object here, the X, has to have a utility that is below 1, okay? So that's basically the proof. And as you can see, the quasi-convexity of this indirect utility, right, which is a shape constraint on the indirect utility, doesn't need that the utility is concave, right? It only needs that you're maximizing an object subject to a budget line, okay? So the fact that the linear budget is linear will basically make this indirect utility quasi-convex, okay? And we will understand this even more when we go to the expenditure function, right? But we are not there yet. Perfect. So again, the indirect utility is an important object that will be used for welfare evaluation, okay? This is one key job of economists. So for instance, when you are hired by the World Bank, and then they want you, for instance, to do a tax evaluation. For instance, how do governments know which tax scheme is better, right? So you want some objectives, such as we want to collect certain amount of money, right? But we want to do it with the less distortion possible, right? And then basically you are asking a welfare question. So how do I make a tax scheme that reduces welfare losses, right? By given my budget constraint. So given that I want to get certain amount of income, okay? So if you have that objective, essentially you have to deal with indirect utilities. So indirect utilities are the object that you would use to evaluate the different tax schemes, right? So remember that a tax scheme is basically a change in prices, right? Or a change in income. And so therefore the indirect utility is the object that will allow me to rank prices and income. So hence it will be used to evaluate taxes schemes of different taxes, right? Do you understand? So that's the interest of this object. And right now we know some properties of this object, mathematical properties, okay? Now, as we progress through this chapter, there is this famous Roy's identity, okay? So the Roy's identity is yet another phase of rationality. And this phase is very interesting because it's more of an econometrics phase, okay? So right now, and we discussed this in the summer, I mentioned that a way to understand completeness and transitivity, right, is basically that you can project any complex choice element into a real line, right? Because the real line is basically the object where you can have a natural order that is complete and transitive, right? That's essentially what a utility does, right? Projects very long, for instance, fractional trading baskets, even with thousands of stocks, right, into a single number, right? So basically, we are able to rank any complex, potentially large vector of alternatives into a single number, okay? So that's what is rationality. So this is another way, in a more differential, using calculus way of describing that phenomenon, that essentially utility maximization is a technique to reduce dimensionality, right? So from an econometrics perspective, that can be very useful, and I'm gonna make that clear in a second. But for now, let's describe what is the Roy's identity. So the Roy's identity essentially asks the following question. It asks, what will happen with the indirect utility if I change my parameters? What are my parameters in the consumer problem? The price and the income, right? So I have an optimization problem, and this optimization problem is indexed by the parameters P and W. So as I change the parameters of the problem, my solution is going to change, right? So there is a formal way to study how the indirect utility, which is the solution to the problem, right? The objective function evaluated at the maximum, changes with the changes in parameters of the optimization problem. And the way to do it is something that's called the envelopes theorem. So the envelopes theorem, right, is a result in math and in optimization that sometimes you prove it in the math class with Maria, sometimes you don't. There is also a proof in this book by F.A. Ock of Real Analysis for Economists. So the envelopes theorem proof is not the objective of my class. I will just take it as given, and I will state it, how it works, and then I will just use it in my problem, right? So the envelopes theorem basically says that I can do the following to obtain the solution to what is the change in the indirect utility if I change income, and what is the change in the indirect utility if I change the vector of prices, right? So first, say that I have my indirect utility and I want to know how indirect utility changes if I change the income, right? So this is a classical question, right? So if I change your budget by increasing your income, how much the welfare you derive from the problem will change, right? So that seems very complex, right? Because I have to first optimize the problem, obtain the demand, then from the demand, see how your demand changes with the income, use the marginal change in consumption and map it to the utility and see the change in utility. All those steps are summarized by the following derivation, which is super simple. Write down the Lagrangian, so u of x plus lambda parentheses w minus p times x. And once you have that objective, assume the x is constant, right? So you can assume, this is the envelopes theorem basically saying that you can assume that the control variable, so the x is constant, and then just proceed to derive the Lagrangian as if the x was constant with respect to the parameter, okay? That's the content of the envelopes theorem. So let's do that mechanically. So write down the Lagrangian, u of x plus lambda, parentheses w minus p times x. Assume the x is constant, right? And now derive with respect to w. What is the derivative of the Lagrangian, assuming x is constant with respect to w? Who can tell me? Well, super simple, right? It's just lambda, right? So that means that the change in the indirect utility with respect to income is equal to lambda. So this is a cool result because it's telling me that the Lagrange multiplier, right, is essentially measuring, how does my change of income affects my welfare. And this gives a new name to the Lagrange multiplier, which in consumer problem and in this chapter is basically the marginal utility of income. Okay, that's a pretty cool name, right? So basically we're saying that lambda essentially measures what is the marginal utility of $1 more. Do you understand?
Yes. Sorry, Professor, can you a little bit slower? Very fast. But it's clear. It's clear, but I just writing. Sorry.
Yeah.
You said, sorry, you said marginal. Yes, you said marginal
utility of income.
Yeah. Thank you.
Yes. So yeah, there's a lot of new results here because essentially we're using a new math result, right? And this is the envelopes theorem. So the envelopes theorem, right, as I was telling you, basically allows me to do this magic. So, mathematicians prove this and essentially tells me, look, if you want to know how your objective function, right, changes with the parameters of an optimization problem, here the indirect utility changes with prices and income, you can write down the Lagrangian, right? Assume the x, the object that you're maximizing, is constant, right? And derive with respect to the parameters. That's it, right? Now, the intuition of the proof essentially is that the algorithm I described, right? So first, maximize the problem, take the demand, derive the demand with respect to income, right? Then map the change in demand to the changes in utility, right? All of that is equivalent to basically maximizing the Lagrangian, assuming the x is constant, right? Because originally what happens, right, is that as you change the parameters, you can assume that the x is fixed, right? Because this is a marginal change, right? So now once you do that, then now essentially you can assume the x is constant, then you can maximize the Lagrangian. In this case, if you do that, deriving with respect to income, the indirect utility is going to give you that is equal to lambda. Okay. Now lambda is, of course, you call it the Lagrange multiplier, right? Now I'm telling you, under this new result, we can also call it the marginal utility of income, because it's telling you how the indirect utility changes with a change of the income. Or if I give you $1, how much it will change your welfare, okay? And this is equal to this lambda number, okay? So now, the second part, okay? So now prices. So here you see the symbol that we have seen before. This is this nabla. So this is a vector of partial derivatives, right? So this is the gradient. That's another way to call it. So essentially, this is a vector. In each entry, there is a partial derivative of the indirect utility with respect to the price. So the first entry of this nabla object is, for instance, entry of this vector 1 is going to be the partial derivative of the indirect utility with respect to price 1. Okay, do you understand? So this is of size L times 1. The previous one is just a scalar, right? This instead is a vector. So remember, this object here is a scalar object, right? This object here is a vector, okay? And this is equal to what? Is equal to minus lambda, which is a constant, right? Times x. X is a vector. So what this is telling you, right, is that the marginal utility of welfare, right? The marginal utility change of a price, right? Entry-wise is basically constant with the minus factor, right? Minus lambda, which is a positive number, times x. So all of this is essentially what is the sign of this object, entry by entry. Lambda is positive, we know that, right? The Lagrange multiplier is always positive. X can be positive or zero, right? Because it's a quantity that we assume is positive or zero. And then there is a minus on top, right? So this means this object is always or minus or zero. Do you understand? Okay, so now pause there. Now let's go back a little bit to the indirect utility part. So remember that I mentioned this result too, right? It says indirect utility is strictly increasing in W, right? And non-increasing in PL, okay? So bear that in mind. Let's go back to these derivatives. So the first part.
Can I ask a quick question?
Yep.
So in the second first order condition, when we take the derivatives of the indirect utility with respect to the vector of prices, what will be the name of the economic concept of each of the elements in that vector? So it is the derivative, each of them is the derivative of the indirect utility with respect to each of the prices. So
Yes.
what is the economic concept of that?
Yeah, there is no actually name for that, right? But if you want, that would be the marginal utility of price, right? So it will be if you change price by $1, right? It will map to welfare, right? So this will be if you want the marginal utility of price. But people don't call it that, right? Because the marginal utility of income is more significant, right? But if you want to call it something, that would be the name. And yeah, as you can see, right? This is essentially what Martin described. So is the marginal change in welfare as you change marginally price, okay?
Excellent.
Okay. And then as you can see, the lambda was strictly positive, right? We assume from now on that it's strictly positive, so hence you have that the marginal increase in the utility is a strictly increase in income, right? But the second derivative instead, it can be strictly negative or zero, right? If x is zero, right? Hence is not increasing in price, okay? So here you see the reason. Now, why then these two results are stated differently, separately? Well, this is a way to prove statement 2 in the previous proposition, right? But right now, the Roy's identity is even more powerful. So we're gonna get more out of the envelopes theorem, right? And essentially the punchline of this part is this result. So the Roy's identity says that take the ratio, right, of the vector of the marginal utility of prices, right, and divide by the scalar object the marginal utility of income, and then what do you get back? You get a demand, okay? So this result works for differentiable demand, that is also demand function, right? So this result only works under differentiability and uniqueness, right? So this result doesn't work in this form when you have demand correspondences. Of course, if you go deeper a little bit into the theory of consumer theory, there is a version of the Roy's identity for sets and demand correspondences, right? That is too complex for this class, so but bear in mind that there is a version, right? But in this particular case, right, we're going to assume on top that is differentiable and unique, and hence there is a demand function. And now under those two assumptions, right, we're going to get that you can recover back the demand function as basically the ratio of the marginal vector of marginal utility of prices, which is a vector, divided by the scalar marginal utility of income. So if you divide these two, you will see that the lambda, which is a strictly positive quantity, gets canceled out, right? The important thing again is that the lambda is strictly positive, okay? Now, so this is cool. This is math that is cool and seems magical. So it's really cool. But the important thing is this. So now let's go.
Sorry, Professor. So this technique, is it like, we can say it's like comparative statics technique?
Yes, it's a comparative statics technique. And essentially the envelopes theorem is a differential version of comparative statics. There is something that of course doesn't require differentiability, and that's something deeper, right? That's called robust comparative statics. But this comparative statics version is the more easy one, and this delivers this result. So the first two are just comparative statics, and then combining them, that's just a lucky finding, right? So this doesn't work in general, right? But it works for consumer theory, right? That deriving the changes in prices and income gives you back the demand. But importantly, here is another intuition about rationality. What I'm telling you here is the following. So what is the demand function? So always have in mind that we're studying an object that is very complex. So in our example with fractional investment, right? You can have, for instance, 1,000 stocks, okay? So the consumption basket can be a vector of size 1,000, okay? So the demand object, right, is basically a mapping from 1,000 prices and an income level, right, to 1,000 quantities, okay? This is the object you have. Now, So for now, say I hire you, I'm an investment company, right? And now I basically tell you, look, I have this data for fractional trading, so a basket of goods, of different stocks, and I have these 1,000 prices, right? And I have a bunch of different trading days with different prices and different quantities, right? And I have different incomes, right? Now, model this, do the demand function. So this is an econometrician's problem, right? So what is your output? Is X, the quantity, right? What is the input or the independent variable? Is prices and income, right? Forget about now endogeneity and other issues. So this is a classical regression problem. So you have X quantity versus prices and income, right? Do you understand the dimensionality of this problem? So essentially, right? Imagine you have, for instance, 30 trading days, right? So it's a small data. So you have hourly data, right? So you can multiply by the hours. So this is your data set, yeah? And in each of those trading periods, you have basically a vector of 1,000 goods, right? Versus 1,000 prices plus the income, right? So you essentially have a huge demand system, right? A system of equations that you have to fit using some model, okay? So now, what would be one way to deal with this? For instance, we can write down a polynomial model, right? So I say the demand for stock L, versus imagine stock L is Moderna, right? And now it's getting a lot of interest, right? Because of all the innovation they are making. So XL is Moderna. Now you write down a polynomial model. So this is alpha 0, right? A constant that is indexed by L. So I allow a different intercept per alternative, right? Per good. And I have 1,000 of them. And then, I have, imagine for now that income is even, for simplicity, is 1, right? And this particular example. So no income, even to simplify stuff. But it still is very complex because now I have to also model with respect to prices. So now imagine, so you remember that the stock demand not only depends on its own price, right? But also on the price of other stocks. Do you agree? So essentially, and why not? All the prices matter for this demand. And I'm making a super simple model, right? Where I have basically kind of a Cobb-Douglas kind of style. So alpha K, which is a coefficient, indexed by each stock, right? And now this is running from 1 to L, so from all goods, right? And now the price itself has an exponential, so making it not linear, such that this is beta K, and also is indexed by L. So in other words, right, if K is different from L, this is a cross substitution pattern. And if K is equal to L, is the own substitution pattern. Okay, so this is a model, and you can find any other models that you want. This is a polynomial model. Okay, good. And this is the one I want to make. Now, how many parameters do you have here? So you have the constant, right? And you have 1 per stock. So you have 1,000 constants, right? And now you have 1,000 times 1,000 alphas, right? And the same thing for the beta. So this is a huge model, right? It's a super flexible, super huge model with lots of parameters. So in general, this is the problem of high dimensionality, right? So you have a huge number of alternatives or goods, and then you have a huge number of dependent variables of prices. And you can see that it can get quickly very large. So now what do you do with that model? So imagine you're a machine learning guy, right? So, and you say, okay, I'm gonna use something like lasso, right? You know what this lasso is? A regularization technique that basically is trying to pick what betas are not 0 and what alphas are not 0, right? So essentially I can create a statistical penalty and try to kill some of the alphas and betas, such that not all of them are positive, right? So I have a more sensitive model. And that's called reduction of dimensionality. So essentially I'm saying, look, in real life, the stock price of Moderna will depend more on the stock price of Pfizer, but not so much in the stock price of cement, right? Do you understand? So there are some stocks that are more related to others, right? And sometimes there are some stocks that are not related at all with others, right? So, and then basically the idea would be to reduce dimensionality by killing that, right? Now, so that's a kind of a statistical way of dealing with reduction of dimensionality. Here in micro, and we provide you a different way to do that. And essentially the way to do it is through a utility function. So you say, look, in the end, these stocks, the behavior that you see is the product of utility maximization. That's my working hypothesis right now, right? I'm going to assume, and there is a cost assuming that the investment that I observe in my data comes from utility maximization, right? If that is the case, and there is a test for that, so imagine that test was passed, how can I model this data? And I say, for instance, look, since even if you have 1,000 stocks, they are going to be mapped to a single number, which is the utility. Let me model now the indirect utility directly, right? And now what you're going to do is write down the indirect utility with a statistical model. And this indirect utility, again, let's fix income to 1 for simplicity, is a function of all prices, right? From 1 to L. But importantly, right, there is only a single scalar value instead of 1,000 indirect utilities, right? That's the magic of indirect utility. There is only one scalar value. You can project any huge vector into a real line, right? And now write down this object. And this object, for instance, I'm gonna use a classical model this is a semi-polynomial model that is essentially alpha LK multiplied by PL to the 1/2, PK to the 1/2. This is a very flexible model that turns out that we can approximate any demand function up to the quadratic approximation, right? So it's a very famous model that was used previously when we have more issues with computers. But what I want you to see in this even very simple model is that now I can use the magic of Roy's identity. So take the indirect utility, right? And remember that because I'm fixing income to 1, the marginal utility of income is 1. So here it doesn't play any role, right? So the only thing that matters here is that the XL is equal to the partial derivative of this polynomial indirect utility model with respect to PL, okay? So once you do that, right, essentially you build yourself a system of equations that depends only on a scalar value, right? And all the whole vector of the 1,000 goods, is a partial derivatives of your scalar model. So when you're feeding this model, you don't have this huge number of parameters. You only have the alpha LK, right? Which is 1,000 times 1,000. So you reduce the dimensionality a bunch, right? And you make the model much more tractable. Now, this is another way, if you are more econometrics driven, to understand rationality, right? Rationality is essentially an exercise in reduction of dimensionality, right? Out of the many criteria you can use, whatever they are, they're going to be mapped into a single scalar value, right? And importantly, we already proved that this indirect utility is quasi-convex, irrespective of whether your utility is convex or not, right? So you can focus your attention on using convex models here, right? So there is a lot of structure that the utility maximization problem gives you, okay? So I'm going to stop here because this is not a class for econometrics, but you can see how the Roy's identity matters, right? So the Roy's identity essentially tells you that under rationality, the demand vector is essentially, in physics, they call it a scalar field. And don't be afraid of the name. A scalar field basically means that you are the derivative of a scalar function, okay? So what it means, right, is that if your vector behaves as being controlled by a scalar function through a derivative, that's a scalar field, right? That's from physics. But the important thing here is that essentially, your 1,000 consumption behavior is reduced to a single object. The force behind it is called utility. And if you recover the scalar object, you know the whole behavior. Okay, great. So that's rationality. Again, this is at the same time really cool, and at the same time a little bit concerning, right? Because you should say, wait a moment. So you're telling me that 1,000 stocks can be modeled by a single scalar criterion. Maybe you're a bit too optimistic. And this is the matter of discussion of the current literature, right? Is this really the case or not? For instance, I will argue the following. So imagine, you're a trader, that is not very sophisticated. You like to play with stocks and so on, right? maybe, you know, just because you are not that sophisticated and you're a human, right? You have just one brain. You know, the fact that your brain is limited such that you have to project huge amounts of information into a scalar value, right? To say this, you know, portfolio is better than this other because it gives me higher expected return, right? Then, you know, that's obviously a case where you are being a scalar by construction, right? Because you are measuring expected return, right? Now imagine you have a convex combination of expected return versus variance, right? That's another example of you being unidimensional, right? Because you're making a convex combination of two objects, and in the end, you're making it one. Now, but imagine now that you are a more complex investor, right? For instance, you are part of a hedge fund, right? And the investment is not done by one person, by a board, for instance, right? Many people are deciding, right? Then you enter the same thing as a problem in households that we discussed in service, right? Many people voting what things you should buy and what things you shouldn't, right? So then becomes multi-criterion, right? And essentially, the more complex the decision making becomes, you know, is a little bit less likely that you can actually think of this as being just a map to a scalar function, okay? But this is the force of rationality, and it's both a blessing and a curse, right? It's a blessing in the sense that it's gonna make any complex model very simple, right? But it's a curse in the sense that it may be sometimes too simple, right? And that's a little bit the current research, okay? If we can model, you know, complex behavior such as investment using just a single scalar object, okay? But that's the Royce identity here, okay? Any questions here?
Yeah, can I ask you something? So I understood the concept of what you're doing, the reducing the dimensionality from L to 1. Is that more or less? So
yeah.
But I'm reviewing the how we got the Royce identity, and I cannot figure out what the difference is with the standard utility maximization problem. For we are still maximizing the same utility function, but instead of taking derivatives with respect to quantities or to goods, we are taking derivatives with respect to income and prices. So there you are still working with the high dimensionality, if I'm not wrong. And then you get the Royce identity. So I don't get how you are actually like reducing the dimensionality of the problem.
Yeah, so what I'm saying, right, is essentially the following. Is the Royce identity is just a result of comparative statics, as Irina well put it, right? It's telling you how the objective function changes with the parameters of the problem, right? And what you're doing, as Martin well points out, is you're taking 1,000 derivatives, right? So in that sense, it's high dimensionality. But what I'm telling you is that, and I was illustrating this with these two models, so model 1 and model 2, just by counting, simple counting, right? Model 1 has way more parameters than model 2, right? So in general, right, model 2 is giving you discipline in the sense that it's telling you, you are the derivative of a scalar function, right? If you do that, that's called a scalar field, right? And that's a model of way less dimensionality than a model where the vector system of equations, that is a vector system of equation, is completely unrestricted. And I was just counting, right? In particular, notice here that the constants, for instance, right, are going to be 1 per good, right? So in general, right, so what I'm saying between model 1 and model 2 is that model 1 is just a huge number of parameters, right? Because they don't have any discipline, right? They may or may not come from utility maximization. So in this particular example, I'm just telling you that this translates to the fact that you may have a huge number of parameters, right?
Mm-hmm.
Okay. And once basically you assume that you are being utility maximizer, it means that you can map any vector, however big, however large, into a scalar function, right? And we use that fact here to make a model coming from the derivation, right? That essentially delivers a reduced model, right? It's just one particular application of the Royce identity, but it doesn't mean that it's still easy to do computationally, right? It's just smaller than the unrestricted problem. Okay.
Okay, I'm gonna ask something very stupid, but how do you get the XL and the V here, the ones of the models that model 1 and 2? I don't get it. Sorry.
No, this is an arbitrary model I made from models that people
Okay.
have used in the literature, right?
Okay.
I was just making a point in this particular example, right? And
Okay.
let me label. It's labeled as an example, right?
Okay.
Essentially, it's a special case of the further, more general Royce identity. Okay.
Okay, my question was, sorry, if I want to solve the one particular utility maximization problem in paper, say, is there a difference between going through the one approach or the other, that is the utility maximization framework, the standard one, and the Royce identity?
Yeah, so there is a difference. So, for instance, what people do actually in applied work is that they never write. So in very few cases, they write down a direct utility, right? And try to solve and get the indirect utility from the direct utility. They don't do that.
Mm-hmm.
So we know the properties of the indirect utility. We know they are quasi-convex. In general, people do convex preferences. We know they're homogeneous of degree 0, right? We know they are continuous and so on. We know they are strictly increasing in income and we non-increasing in prices, right? With these properties, turns out, if you write down any model that satisfies the properties I just listed before, right? That's enough to have a model that is as if it comes from a direct utility and you maximize and you get the whole thing. So what people do in a matrix actually is write down the indirect utility in terms of prices and income, right? And satisfying the properties I described. And that's a guarantee that there is an underlying indirect utility that if you maximize subject to the budget will give you that indirect utility. And the reason is that in data, you see quantities, you see prices, you see income, right? So hence what you're actually modeling is everything in terms of the dual, right? And the way you connect observations to prices and income is through the derivative. So that's actually the approach of the almost ideal demand system by Ditton and Neubauer, right? That they won the Nobel Prize. So they started from an indirect utility, right? And then, which is the almost ideal demand system, and then wrote down the demands by using Royce identity, right? So that's how they do it in real life. And the reason is essentially that if you have 1,000 goods, it's very hard to model the direct utility, right? So very few people do it. And some people do it essentially macro because they have less goods. But for instance, if you are in trade, you're doing, for instance, finance or you're doing marketing, right? Like the data sets I use, you're going to end up with 1,000 goods, right? So then how do you write down an indirect utility for that? Is a direct utility for that? Is it a Cobb-Douglas, a CS? It's very complex, right? So instead, you write down these polynomial systems that satisfy all the conditions and do non-parametric objects. But even if they're non-parametric, because they are constrained by utility maximization and our theory, right? They give you shape constraints, and the shape constraints essentially that your demand comes from deriving a scalar function, and that's enough to reduce the system and make it more tractable. Okay. Yeah. So again, this is a little bit diverging to something that is not this class, right? But actually, this is part of my research and also people like Roy. Okay.
Sorry, Professor, a very quick question. So when you say about scalar object or scalar function, so if this is a beautiful example, what you're giving about the behavior of stocks. Who is doing such models? Is it financial econometrics?
Yeah, so for instance, people like Lars, Professor Lars here, Stentov. So for instance, he does financial econometrics and he does models of the stock behavior, right? So what people do, is both problems, right? So how do you explain the stock behavior? So who chooses what? And also another part of financial econometrics is, for instance, trying to match the stock behavior of essentially some stocks you want through cheaper stocks, right? That's another thing, which is portfolio designing. But so a little bit, it's a little bit, this thing I'm mentioning is an intersection of consumer empirics, right? With financial econometrics, right? And essentially, these large models become more common because now, for instance, we have richer data sets, right? So the same kind of models appear now in marketing and so on, okay? So versus, yeah, okay. Now, let's introduce the expenditure minimization problem. And this is a pretty cool break if you want, because we're going to give a little bit more meaning of some things we have been seeing. And this problem is essentially what is called the dual problem of the utility maximization problem, And the objective of this problem is really a complement of the utility maximization problem. I'm going to describe the problem and then I'm going to motivate it. So this problem essentially asks, take a consumer and tell the consumer a target utility, right? So the utility has to satisfy a certain level of utility, and this utility is going to be U bar. Then I'm going to ask the consumer to do the following. Minimize the expenditure, which is the multiplication of prices times the consumption. And the control variable, sorry, is X, the same as before. So you're choosing the optimal bundle. Subject to what? To the utility that you obtain from such a basket being greater than or equal to the U bar, okay? So this problem, is describing a hypothetical situation, right? Where you give the consumer a target utility, and then you ask the consumer to minimize the expenditure to satisfy that target utility, okay? Now, this problem is called the dual of the consumer maximization problem, because in the consumer maximization problem, you instead give the utility a budget, right, a constraint, and ask the utility to maximize utility, right? And in this case, instead, you give the utility a target utility, and then you ask them to minimize the budget, right? So essentially, this is kind of the mirror image problem of the utility maximization problem, okay? Now, important thing to know is that the expenditure minimization problem, you can never really observe it in real life, right? Because I can never really see utility, right? So this is going to be an issue, okay? But the interest in this problem is purely theoretical, and it's going to help us understand the utility maximization problem, okay? So we're never going to observe the results of the expenditure minimization problem, but we're going to be able to use the results of the expenditure minimization problem to understand the utility maximization problem. Okay? Okay. So everyone can hear me okay?
Yep.
Okay. Okay, so suppose that the utility is a continuous utility function representing a locally non-associated preference relation defined on the consumption set and the price vector. And then we have the following results. X star is optimal when the utility maximization problem, when W is positive. Can you hear me? Alex, can you hear me? Yeah, okay. Good. So,
Yep.
Great. So if X is optimal in the UMP, when W is positive, then X is optimal in the expenditure minimization problem, when the required level of utility is UX. Moreover, the minimized expenditure level, P times X, is equal to W. And this is exactly the income level W. So this is telling you that there is this connection between UMP and EMP, okay? The second is, if X is optimal in the expenditure minimization problem, when the required level of utility is U above some U0, then X is optimal in the UMP, when wealth is equal to P times X star. Moreover, the maximized level U of X star is equal to U is exactly the U bar level, okay? Now, the proof, is essentially very simple. It comes from Mascolel. It's telling you that these two are the mirror images, right? And essentially, what this is telling you is that if you fit the optimal indirect utility to the expenditure minimization problem, and you solve it, the demand that you obtain from the expenditure minimization problem is the same as the Marshallian demand that we studied, okay? Now, the other part, if you take the optimal expenditure level, you feed it as part of the budget constraint to the utility maximization problem, right? And you obtain the budget, the solution to the UMP, you obtain the optimal bundle that you would have obtained from the EMP, okay? So these are basically mirror image problems. And then we're gonna use this fact to learn more about the UMP. Important part. So expenditure function. The expenditure function, right, is a mapping. You do it like this, so we are clear. From the space of prices and the space of utilities, which is the real line, right, to the real line. Okay. And this is
Victor, one quick question. So proposition 11 is the duality theorem, right?
yes.
Okay.
So the expenditure function, right, is essentially the optimized value of the expenditure minimization problem. So it's the exact analogous of the indirect utility. Okay, and this is denoted by E, and is E of prices and the utility bar level, or U, and this is equal to P times X star, and X star is the optimal solution to the EMP. Okay. Okay. Now, with this object in hand, we will provide the following properties. Suppose that U is a continuous utility function representing a locally non-associated preference relation defined on the consumption set X. And then the expenditure EPU is first homogeneous of degree 1 in prices. So why is that? Imagine I scale up prices by alpha, alpha being positive. What will happen with expenditure? Expenditure will be bigger, right? By how much? By alpha, because the objective is essentially P times X. So if I take alpha, multiply it by P, my expenditure will be alpha times the original expenditure, right? So this is homogeneous of degree 1 in price. And essentially you can see the proof here. You minimize the expenditure now with an alpha there, the solution will be also multiplied by the alpha. Expenditure minimization problem is strictly increasing the utility. Why? Because if your target utility is higher, what will happen with expenditure required to fulfill that? It's gonna get bigger. Why this is? This is from the local non-association, right? The higher the utility, right? The more, basically the more expenditure you need to fill it, right? So you need to be basically consuming at exactly the maximal level of utility because of local association. And this is also non-increasing for prices for all L. And this, the reason why it's non-decreasing is the same reason of using envelopes theorem. We're going to use it in a second as well. And now, important thing, the expenditure function is concave in prices, okay? So concavity, as you remember, is basically a shape constraint on the on a function. What is a concave function? So remember that if you were looking at one dimension, right? A concave function is essentially a shape of a mountain, right? But you know, more formally, we're going to define it in a second in the multiple variable case. Okay, multiple variable case, we will define what it means to be concave in a second. And turns out that the expenditure is concave, and this is going to be important for properties of the demand function. And finally, it's continuous on P and U. Continuity is not surprised by now, so it's a nice property to have. And we know that this allows discrete jumps of expenditure if I change my price on my U target by a bit. So the proof of 1 and 2 are omitted, are very simple. I'm just going to prove concavity. Okay, so remember, the concavity shape constraint on this expenditure function is very important. I'm promising you this. As we finish the chapter, you will see that concavity plays an important role. And I'm gonna give you the heads up. Concavity turns out to be related to the weak axiom of revealed preference, and also to something called the compensated law of demand. So essentially, concavity of the expenditure function is essentially already gonna tell me that as prices goes up, quantities goes down, okay? And this actually is a consequence of the concavity of the expenditure function, okay? Right now it's not clear yet, of course, but we will make the link clear, okay? For now, let me prove it to you that expenditure is concave. So now we want to show that expenditure is concave. What it means to be concave. So take a convex combination of prices. So say, for instance, I have P and P prime, and call the convex combination of such prices P alpha. P alpha is alpha P plus 1 minus alpha P prime. Okay, for any alpha between 0 and 1. Now, what it means to be concave for any function, for any number of variables, concave in prices means expenditure of P alpha for a fixed U. U is always fixed in all this exercise. It never changes, only price changes, is greater than or equal to alpha of E of the original price plus 1 minus alpha of the second price, okay? So again, the geometric intuition for one dimension is that this is a mountain, right? Okay, so if you take the convex combination of two prices, then this is gonna be above the others. Now, of course, I'm not gonna throw it because then you're gonna always think only on the one-dimensional case, right? Let's see the definition because we're dealing with multiple dimensions, right? So the definition is very clear, right? And it just means that if you evaluate the function at the convex price, convex combination price, this has to be above alpha E of P plus 1 minus alpha E of P prime, okay? This is concavity. Now, who remembers concavity of a function using derivatives, okay? So concavity can be detected using second order conditions, right? So from a scalar function that is concave, what happens with the second derivative of such a function? So take an example, right? So what is a classical concave function? Is square root of x, right? Do you agree? Is that concave? How do you know it's concave? Derive it twice, right? So what is the sign of the second derivative of the square root of x?
Positive.
Sorry?
Positive.
Sorry, Irina?
Negative, I think, negative.
Negative,
Yes.
right? Yes. So the second derivative, if you're negative, right? Essentially it's telling you, right, that this thing behaves like a mountain, right? So this scalar intuition will come again. And in fact, in multivariate case, you don't have anymore a single derivative, right? You have a matrix of derivatives, which is called the Hessian, right? And this second order derivative is going to be negative semi-definite, right? And this is essentially the important property we will use that is equivalent to the weak axiom. And yeah, so essentially, Martin, you know, it's an easy error to make because, you know, if you are convex, is exactly what you say, right? So usually these are the mirror images, and then usually we remember in math they teach you the convex one, right? While the concave is for micro. Okay, so let's keep going. So now I want to show this. I'm going to use the following notation. I'm going to say H of PU is the minimizer of the EMP. So when you see H, this is called in Mas-Colel the Higgsian demand, right? So Mas-Colel likes a lot of historical names, right? Higgs was another famous economist, right? And Higgs, you know, we call the Higgsian demand the solution to the expenditure minimization problem. That's why we use the H, right? Nothing fancy about that symbol, it's just the historical name. And I've used a little bit notation and let it denote any element of the set of optimizers, right? So we're assuming for now effectively during the proof that you have a Higgsian demand function, not a demand correspondence. However, the proof works for demand correspondences as well, right? We're just gonna simplify our life assuming it's for now a function. So the Higgsian demand function, right, has the following property. The expenditure, which is the optimal value of the P alpha, is equal to P alpha times H of P alpha U bar, okay? So that means, right, that the expenditure function is equal to price times the Higgsian demand. Do you agree with this? Very simple, right? Because the objective is just the multiplication of prices and X, right? When I obtain the optimal Higgsian demand, H, if I multiply it by price, I obtain the expenditure function. Okay, so nothing fancy here. Keep going. Now, by definition, this is equal to, what is P alpha? Is the convex combination of prices, right? So alpha P times h of p alpha plus 1 minus alpha p prime times h of p alpha. So notice that I expanded the p alpha using the definition of p alpha and nothing more. Do you agree with that step? I just expanded p alpha, nothing fancy. Okay. Now, here comes the key step. It's very subtle, so pay a lot of attention. Remember that an expenditure function is a minimizer, right? A minimizer, okay? So that means that if you take expenditure at P, this is equal to P times the Higksian at P, right? And because it's a minimizer, it has to be less than equal than P times any other demand, right? At the level, remember U is fixed all around, right? So U bar is always fixed, never changing, right? So the only thing that's changing is prices here. So if I take the Higksian of P alpha, right? That has to be above, weakly above the H of P. Because remember that at prices P, what is the minimizer of the expenditure? Is H of P, right? So H of P alpha has to be weakly above because it's not longer a minimizer. Do you understand? So by definition, the minimizer has to be below everything else, right? And H of P alpha is something else, hence has to be above. As simple as that. Do you understand?
No, there is something I don't understand. So
Yeah.
the Higksian demand is by definition the minimizer of the EMP. So
For a given price.
okay, so we are changing the price, right?
Yes.
That is what we're
yes.
doing. Okay.
Yes.
Sorry.
No, great question, Martin. Great question, Martin. So the important thing, and this is a little bit tricky, right? Because here the symbols look almost the same, but in the right-hand side, there is a P alpha, right? And in the left-hand side, there is a P, right? The expenditure is the minimal amount that you get, right? In terms of money that you are spending to get your U-bar at prices P, right? Hence, if I change the Higksian demand, which is a function, and evaluate it at a P alpha, for price P is not longer the minimal quantity, right? So it's something else, okay? And of course, it can be equal or it can be above. Do you understand? Okay, just because the P times HP is the minimal object, okay? Do you agree? Yeah. So bear in mind that inequality. That's the key for the proof. Now, go back to the expansion, okay? And look at this object. So you have P times HP alpha, okay? But PH times P alpha, I already wrote an inequality. So I know that P times HP alpha is greater than or equal to P times HP. Do you understand?
I don't get why the inequality includes it is not a strict inequality.
Because it can happen. Remember that the alpha goes between 0 and 1, right? So we're allowing the case where P alpha can actually be equal to P, for instance, right?
Well, okay. So if we exclude that case, it is strictly unequal, right?
I think it might be for some cases, but I don't think in general we can be sure of that because there can be very weird utilities. But I guess maybe your intuition is right. But for the proof, it doesn't really matter, right? So we're gonna keep using that inequality because that's covering all cases, right? So even if your intuition is true, I don't think it would change the result. In other words, okay? Yeah. So I don't know, but I don't think it actually affects the proof. Now, so when you have those two things together, now remember that this expansion that was an equality now is transformed to an inequality, right? Because the HP alpha, because term by term, this term here, is dominating the one with the HP, right? Now you observe here there is alpha P times HP, 1 minus alpha P prime times HP prime. So this is, of course, element by element below each of these elements of the summation. So that means that this term here is weakly above the convex combination of the expenditure at P and at P prime. That's showing concavity. Do you understand? Okay. So the proof is very simple. It's only using the fact that the expenditure is minimal. And again, this is in general a mathematical regularity, if you want. So if you are minimizing linear objectives, so this is p times x, right? So it's linear in the x. Do you realize that? So it's a linear objective. So there is no exponent to it, right? It's just p, which is a coefficient, it's a parameter, times x. No? So if you are maximizing with respect to that, you are minimizing, sorry, a linear objective. So if you take the minimum of many linear lines, then you're gonna get basically a concave object. Okay. So we are gonna go deeper into that property, which is called a concave envelope, right? That's a geometric thing. Doesn't matter for now. The important thing is that if you minimize linear objectives, you're gonna end up with concave objects. That's kind of the punchline here, and we prove it right now. We minimize the expenditure, which is a linear objective, right? You end up with a concave objective function. Okay. So everyone's happy with that? Yeah. Okay. Good. Now, continuity in P and U follows from the Berg's maximum theorem. We already used it before. There is a slight trick that you have to do. So in order to show that the Berg's maximum theorem applies here, remember that it was about optimizing a subject to a closed unbounded constraint, right? But the constraint here is not bounded, right? But what you can do is basically bound the constraint by realizing that because of Lockean association and continuity, you must consume at the frontier when the utility of x is equal to u bar. And that essentially will compactify and make closed unbounded the budget. It's not a budget constraint here, it's just a constraint, right? So instead of the weak inequality, you are going to have the equality. And in that particular case, remember that we can do this because minimizing the expenditure, we can create a non-binding upper bound, right? And by continuity, we can make it equal to u bar. So this is called the no excess utility. And essentially here the proof, the last part, is showing that you have to consume at the limit, so it's equal to u bar, and that basically will allow me to create a compactified constraint, which will allow me to apply the Berg's theorem. So this is a little bit of playing with math to basically show that the utility is continuous on P and W. Okay. Now, so these are technical properties. We're done with that, and now let's make a stop to proceed to the Higksian compensated demand. And remember that the Higksian demand was the solution to the expenditure minimization problem. Suppose that U is continuous and it represents a locally non-associated preference. Then the Higksian demand correspondence HPW has the following, HPU, sorry, has the following properties. Is homogeneous of degree 0 in P. Okay, why is that? So essentially, right, even if you scale up the objective by alpha, right, the solution to the problem is going to be exactly the same in terms of quantities. It's just that you spend more, right? But you're going to end up buying the same quantities, but paying more, okay? So in that sense, remember that expenditure was homogeneous of degree 0, homogeneous of degree 1, but the Higksian is homogeneous of degree 0, okay? The second property that we already observed in the previous part is that there is no excess utility. That means that any optimizer of the expenditure minimization has to hold with the quality. Why is that? Because remember that Lockean association means that if you're consuming above the target, you're going to be spending more, right? So you have to consume exactly at the target. So whatever optimum level or minimizer in this case of the expenditure problem has to be at the U-bar level. And finally, as usually, Mas-Colell style, Mas-Colell throws you in the additional assumptions. So if preferences are convex that we discussed the previous class, then the Higksian demand is a convex set. Okay, that means in other words that the demand corresponds is convex value. Okay, and if the preferences are strictly convex, then the Higksian is a unique element. Hence, you have a function instead of correspondence. So nothing new here. In the last minutes, let's go through the Karush-Kuhn-Tucker for the expenditure minimization. In this particular case, you will see that this is just another application of Karush-Kuhn-Tucker. So write down the Lagrangian, P times X minus lambda of the constraint. The constraint is Ux minus U bar. First order conditions are P greater than or equal to lambda multiplied by the partials of the derivatives of the direct utility. And then you have the complementarity conditions, right? So XL parentheses the first order conditions, okay? And so that's it. Nothing new here. This is just Karush-Kuhn-Tucker. Now, what is the analogous of the Royce identity, but for the EMP? It's called the Shepard's lemma. Shepard's lemma here is even easier. So just use the envelopes term. So write down the Lagrangian, P times H plus lambda of the Lagrangian, parentheses UH minus U bar. I'm never going to derive with respect to U bar, so that's not here. I'm just going to derive with respect to price. U bar is always fixed. So derive the expenditure with respect to price, assuming H is constant, another application of the envelopes term. And now what do you get? You get that the gradient of prices of the expenditure is equal to the Hicksian, okay? And this is called the Shepard's lemma. This is really cool because this is telling you again, the same intuition, that the Hicksian demand, or whatever you choose to consume for a given target U bar for a big vector of prices, is going to be a vector of derivatives of a scalar function. Now, why we study this? Well, remember that the E is the expenditure is a concave function, right? So if you derive twice a concave function, what do you get? You get a Hessian, right? A matrix of derivatives, which is called a second order derivative, which happens to be a negative semi-definite. So I'm going to explain this in a second, but this essentially tells you something very cool, which is studying the comparative statics of the expenditure function are really rich and simple. In particular, let's introduce this object, capital D with a sub P of HPU. And what is that? First of all, what is this object? So this object, as you can imagine, is the Jacobian of the Hicksian demand. Okay, who remembers from calculus what is a Jacobian? So Jacobian, right, is a matrix of derivatives, right, with a entry KL, right, equal to what? Equal to the partial, right, with respect to price L, right, of demand K, right? Do you understand? Okay, so it's a matrix of derivatives of a vector function, right, where entry KL is equal to the entry K partial derivative with respect to variable L. Okay, and this is essentially entry KL. Okay, so now this object here, of what size it is? So you have L goods and L prices, right? So it's of size L times L. Do you understand? So it's a square matrix, okay? And importantly, what is inside the main diagonal? So the main diagonal is whenever K is equal to L. So what do you get there? Is essentially the change in the Hicksian demand of good 1 with respect to the price of 1, right? And in the second entry of the diagonal is the change of the Hicksian demand of good 2 with respect to price 2, and so on. Dot dot dot. The partial derivative of good L with respect to price L. So this is the on price derivative, right? In the diagonal, and in the off diagonal, for instance, entry 1, 2 is good 1 with respect to price 2, right? Do you understand? Okay. So this is the substitution effects, okay? So off diagonal, you are in the substitution effects, okay? And that's why this is also called a substitution matrix, okay? Now, the Hicksian demand function has the following properties. First of all, right? If you take the Jacobian of the Hicksian demand, this is the matrix of Hessians. Hessian matrix of the expenditure function. What is a Hessian? So again, a Hessian of V, right? PU, the entry KL, right, is equal to the partial. So this is double partial with respect to price K, and the partial with respect to price L of expenditure. Okay, so this is a Hessian. So it's the matrix of second derivatives. Okay, so you take the expenditure and derive it first with respect to price K, and then with respect to price L. And that is the entry KL. Okay. So now, why this is the case? So how do I know that property 1 holds? Well, go back to the Shepard's identity. So the Shepard's lemma tells me that a Hicksian is nothing else than the matrix of first derivatives of the expenditure, right? So now if I take this and derive it once again, right, I obtain the Hessian, right? But that's not other operation than taking the Jacobian of the Hicksian. Okay. So again, this is the time you go after the class and check a little bit of your calculus book, right? What is a Jacobian? What is a gradient? What is a Hessian, right? If you don't remember, but nothing fancy. These are all definitions and you will read it in 5 minutes, right? So here is nothing that you should get lost, okay? But I'm already describing them again. Okay, so first property is essentially that a matrix of substitution is equal to the Hessian of the expenditure. Importantly, the expenditure is a concave function, right? So it means that this matrix of substitution, price substitution, is actually a negative semi-definite matrix. Okay. Now, what is a negative semi-definite matrix? Who knows this from linear algebra? Who can tell me? How do I know that a matrix is negative semi-definite?
Professor, it's if you multiply it by a vector and that vector transposed, you have to get it to be greater than or equal to 0.
The opposite, right? You described a positive semi-definite, but yes.
Oh,
so
sorry, less than or equal to 0. Sorry, yes, less than or equal to 0. Yeah.
So let's what Amat said, you know, let's do a little note here. So let's do a little note for that. Negative semi-definite matrix, right? For any vector, right? In RL, a matrix A, right, of size L times L is negative semi-definite if and only if B A. So this is size L times 1, right? So it has to be transpose A, right? B less than or equal than 0, right? So let's check the dimensions to make sure. So V is of size L times 1, right? So if I transpose it is 1 times L, A is L times L, right? And then V is L times L, L times 1, sorry. If I multiply the 3 of them, I get a scalar object, right? Of size 1. And this object, a scalar, has to be less than or equal than 0 for any such vectors. So importantly, right? Negative semi-definiteness is a notion to try to give a sign to matrices. So in scalars, right, in real numbers, we know the sign. So if I give you 2, it's a positive number. If I give you -2, it's a negative number. Now, imagine I have a matrix of numbers. So for instance, I'm going to do a little matrix here. Size 2 by 2. Okay, let me put inside some brackets. So now let me create the following matrix. So what is the sign of this matrix, right? So there is not really a sign because, you know, there are things that are 0, right? Weakly positive, and there are things that are negative, okay? So how do I know that this thing is negative semi-definite? So let's apply the definition that Amat told you, right? So multiply it by any vector V. So what will be the solution to this multiplication, right? So b times a times b is equal to what? It will be the entry b1 to the square, right? Times 4. Sorry, this will be with -2, sorry. Sure. For any b. Okay, do you agree? So that's basically the negative semi-definiteness. Is a way to give signs to matrices, right? And negative semi-definiteness is going to be something that I'm going to use from now on. So, and this essentially follows from the fact that the Hessian is a concave function. And in the last minutes, turns out that this matrix of substitution of prices is also symmetric, okay? And why is symmetric? Because there is something called the Young's theorem that essentially tells me, right, that because of continuity of expenditure, the partials of the partial derivatives of a continuous function, right, are going to be symmetric in the following sense. So if I take the partial derivative of E with respect to PK and PL, and then if I reverse the order of differentiation, right, then it won't matter. It will be the same, okay? And this only holds for continuous functions, right, that are differentiable. If continuity fails, then this is no longer true, okay? Our expenditure function is also continuous. And finally, there is a final property that means that if I multiply the L times L matrix of the substitution matrix times price is equal to 0. 0 here is a vector of size L times 1. And this follows from the fact that the Higgs's demand is homogeneous of degree 0. So if you're homogeneous of degree 0, it means that there is always a redundant good. So remember that because of the properties of expenditure minimization, right? There is always here that the property that this won't change with the scaling up of prices, right? So only relative prices matter because of the Courage-Tucker conditions. Hence, you know, the dimensionality of the substitution matrix is less than full. So it's never full rank. It's always less than full rank. So if you take the determinant of this matrix, it will be equal to 0. In general, it's a non-invertible matrix. It will always have some 0 entries, okay? And this is in particular described as the fact that if you multiply this substitution matrix times prices, this is equal to 0. So who remembers eigenvectors and eigenvalues? So again, this is a parenthesis for linear algebra wizards, right? So the price will be an eigenvector that is associated with the eigenvalue of 0, okay? So hence this equation 4 is essentially telling you that price is an eigenvector associated with an eigenvalue of 0, okay? So it turns out that price is an eigenvector of this DP HPU, okay? And essentially this is another phase of the property of homogeneity of degree 0. So thank you so much. I'm going to